This is columns part 2. At the end of columns part 1, we were talking about radius of gyration. There are two kinds of radius of gyration. There's mass radius of gyration, and there's area radius of gyration. The propeller and baseball bat here, they have mass radius of gyration. If we look at one teeny weeny increment of mass, let's say we pick a little piece of wood that weighs ever so slightly, about like a grain of dust or something, an infinitely small mass of wood from this propeller, and we multiply that mass times the square of its distance from the center of this propeller shaft. And then we do the same thing for every other little infinitesimally small unit of mass in this propeller, and we add all these little masses times the squares of their distances from the rotating axis together. We sum them all up. Then we have the mass moment of inertia. If we could put all the mass of this propeller in one spot, well, actually two spots, one on this side of it and one on that side, so they would balance out. But if we could put all the mass at a certain distance from the rotational axis such that the moment of inertia remained the same, then that distance would be the radius of gyration. The sum of all of the little increments of mass multiplied by the square of their distances to the rotational axis equals the total mass times the square of the radius of gyration. In other words, di, the little teeny weeny increment of moment of inertia, equals dm times, well, they use the letter r, generally maybe we should use the letter h, talking about the distance from there to any given mass. That would be squared. So we sum up all these little teeny weeny increments of mass and multiply each one times the square of its distance from the rotational axis. We add all them together, then we get our total moment of inertia, and it's equal to the total mass. Let's take the total mass of the right part of this propeller times the radius of gyration. We usually use letter K for that, sometimes we use letter R, squared. A beam cross-section, here's an I-beam, this is the cross-section of it, this is what it looks like when you look at the end of it, or if you were to cut it in the middle, that's what it would look like on each side of the cut. A beam cross-section has an area radius of gyration, just as the mass radius of gyration is defined as the radial distance from a given axis at which the mass of a body could be concentrated without altering the rotational inertia of the body about that axis. We can also define our area radius of gyration as the radial distance from a given axis at which the area of a cross-section could be concentrated without altering the area moment of inertia of the cross-section about that axis. These are the dimensions of a W4 by 13. In other words, it's 4 inches high and it's 13 pounds per running foot. This is a structural steel beam. Okay, it has an area of 3.83 square inches. It's 4.16 inches high by 4.06 inches across this way. Okay, the flange thickness is 0.345 inches. The web thickness is 0.28 inches. Okay, but it has a radius of gyration about its x-axis. Let's draw the x-axis here. I think they just say x. And here would be the y-axis. Y. Okay. What we're interested in is the least radius of gyration. And it's going to be this one, about the y-axis. It's going to be right about there. That distance from there to there is 1.004 inches. But the radius of gyration about the x-axis is higher. It's on up here at 1.718 inches. Why is that? Well, look at to the right of this dotted line that goes right down the middle of the eye. We have plenty of area, half of this web, but it's real close to the dotted line, so it doesn't count for much because we're talking about area times the square of its distance to the axis. This area up here times the square of its distance to the axis contributes a lot. So anyway, this is 4.06 inches across, so it'd be 2.03 inches from the center of this eye to here. And the radius of gyration is just a little less than that. It's 1.004 inches. But looking across this x-axis, our radius of gyration is 1.7 inches because we have so much area up here and so much area down here. So the weakest axis, this beam will buckle, like if we were looking at it, it'll buckle this way or this way. It won't buckle that way or like that. It's going to fold over like that or that, not that or that. Back in our gyroscopic precession lesson, we determined that the radius of gyration, the mass radius of gyration of our propeller, was about 55% of the way from the center to the tip. But with a baseball bat, it would be further toward the fast end of the bat. Be sort of like a disc. If we have a disc here, the radius of gyration is going to be 0.707 times the distance between the center and the outer edge, or the square root of 2 over 2. So I imagine, just guessing, I'd say the radius of gyration, if this were the pivot point, it's not. When you're really swinging a bat, your shoulder back here is a pivot point, but if this were the pivot point, I'd guess that the radius of gyration would be somewhere between 2/3 and 70%. Anyway, the radius of gyration is a sweet spot on a baseball bat. That's where hitting the ball transfers the energy to the ball efficiently. If you hit the ball over here on the end, you feel a thud at the handle. If you hit the ball here, you also feel a thud in the opposite direction. Either one's uncomfortable. Hitting the ball right there feels good. The bat just feels like it stops and the ball just flies off the bat. So that's mass radius of gyration. Just as we have both area moment of inertia and mass moment of inertia, we also have area radius of gyration and mass radius of gyration. Mass moment of inertia is typically in units of kilogram meter squared. See, we're taking all these little increments of mass, which are going to be micrograms, but we use kilograms. That's what they eventually add up to. But all these little grams times the square of their distances is going to give us something like gram centimeter squared, or kilogram meter squared. Okay, while area moment of inertia is typically in units of meters to the fourth, because to find the area moment of inertia, we take all these little incremental units of area times the square of their distance from the axis. So area is already a distance squared times another distance squared gives you a distance to the fourth. So area moment of inertia will typically be in meters to the fourth or inches to the fourth, whatever. Okay, at the website efunda.com, let's see, efunda.com/math/areas/radius of gyration .cfm, we can see that the area radius of gyration, kx they call it, of an area A about an axis x is defined as, here we go, area radius of gyration, let's see, well that would be the radius of gyration, that would be the area moment of inertia equals the area times the area radius of gyration squared. Okay, and if that's the case, we can divide each side by a. We have I over a equals k squared. K squared equals I over a. Then we can take the square root of each side. Square root of k squared is k, equals the square root of moment of inertia over area. So that's how you find your area radius of gyration. Just take the square root of the area moment of inertia divided by the cross-sectional area of the beam. Okay, this website also tells us that the mass radius of gyration, right here, that would be this k squared. This k is different from that one. That one's area radius of gyration. This is mass radius of gyration. Well, mass radius of gyration squared times all the mass of the propeller or the baseball bat or the ring or the cheesecake or the disc or whatever equals the mass moment of inertia. And consequently, dividing both sides by m gives you I over m. Take square root of each side and you get mass moment of inertia equals the square root of the, or mass radius of gyration equals square root of the mass moment of inertia divided by the total mass. Radius of gyration, whether it's area radius of gyration or mass radius of gyration, will always be in units of length. It'll be meters or inches or whatever. It'll be the distance between the center of the propeller and there, or it'd be the distance from that dotted line to that dotted line, or that dotted line to that dotted line. It's always going to be a unit of distance, like meters or inches, and that stands to reason because this area moment of inertia, it's going to be in units of something like inches to the fourth. Well, inches to the fourth divided by area, which will be in something like inches squared. Inches to the fourth over inches squared is inches squared, and the square root of inches squared is inches. So that'll be some amount of inches. And here our mass moment of inertia is going to be in units of kilogram meter squared, something like that. So kilogram meter squared divided by mass, which will be in kilograms, gives you meter squared. Square root of meter squared is going to be meters, so there you go. Mass radius of gyration is also in units of length. So that's about all the time we have for part 2. Hope to see you in part 3.